Good evening, this is Jack Wild. This is my response for community problem number 1. I'm going to just walk you through how I'm looking at these problems. I'm going a little bit out of order just because it made more sense for me, but I think I've answered all the questions and hope to get some good feedback. Thanks. Alright, so far in Module 1 we've been looking at how to measure and determine rates of change. We started by looking at rates of change in the physical position of an object because, conceptually, we do this all the time. We're constantly asking ourselves and Google how long it takes to get from point A to point B. And we divide this distance traveled by the time it took almost instinctually. So if it takes me 5 minutes to climb 100 steps, I say that I average 20 steps per minute. And I can express this as a function, and I can graph it pretty easily as a line with slope m equals 20. Now, I never thought about it this way before, but there is a formula that takes this understanding, and I think we all understand it, but expresses it more concisely and clearly. All we have to do is take the function that represents our graphed path and think of it as an input and an output. The input is the value of the x-axis on our graph, and the function itself is equal to the y value on our graph. Now, I don't have a background in math, so I'd never thought about it this way. But one of the interesting things we looked at in this module is that A and B are related. So B can be expressed in terms of A. If we use a variable to represent the interval between A and B on the x-axis, we can rewrite B as A plus this variable. And if your first thought was like mine, it was why bother? Okay, so why bother? Well, let's take a look at this graph again. We know that it's nonsense, right? Sure, we started at point A, and sure, we ended up at point B, and the slope of the line does represent that average rate of change for this trip, but averages are trash. There's all kinds of important data that gets hidden when we look at averages. Rates of change, for example, have a tendency to fluctuate. Different segments of this trip could have wildly different averages than the segment we choose to measure. If you think about it, wherever you start and stop measuring, you're probably excluding data, possibly data that would make a material change to the average. So there's something about averages that's very uncertain and unsatisfying. So instead of focusing on averages, let's take a look at instantaneous rate of change. Going back to our new version of the formula, we can just set h to 0, so that we're only looking at one point. Unfortunately, if we do that, we end up with a 0 in the denominator, which 2 weeks ago was a deal breaker for me. But now, thanks to calculus, I know my limits. Pause for laughter. The trick with limits is that we're going to assume that there is an answer, even when h equals 0. And there are two ways to get there: algebra, and technical term is eyeballing it. So first, let's look at the algebraic method. And we're no longer looking for an average rate of change. Now we're looking for the instantaneous rate of change, also known as the derivative of a function at a given point. And the algebraic method is basically to get the equation to a point where the h doesn't matter. So as h approaches 0, it stops mattering, right? Let's take a function. We'll do g of x is equal to 4x squared minus 8. We can use Desmos to generate a nice little graph for us, but the real work is in the formula. All we have to do is plug the function into our equation for finding the derivative and simplify. So our function reads 4x squared minus 8, so we're just going to replace the x with an a plus h on the left side of the numerator and replace the x with an a on the right side of the numerator. Alright, so next we'll square out that a plus h to get a squared plus 2h plus h squared, and then we'll distribute the 4 across that trinomial. I'm also going to distribute the negative sign in the middle onto the right side. So now I'm going to have 4a squared plus 8ah plus 4h squared minus 8. And then because I distributed the negative sign, I've got a negative 4a squared and a positive 8. So the nice thing about that is that more than half of my terms just canceled out, leaving me with just 8ah plus 4h squared over h. Well, as you can see, you can factor an h out of the numerator, and that h in the numerator and h in the denominator cancel out, so then you're just left with 8a plus 4h. Well, what we're looking for is what happens when h approaches or becomes 0. Let's second part of the equation just disappears and it leaves you with just 8a. So what does that mean? What it means is that for the function g of x, the derivative, or instantaneous rate of change, for any value of x is just 8 times that value, or written, I think, more formally as g prime of a equals 8a. Now, incidentally, that 8a is also the slope of the tangent for any of these points x. So what do I mean by that? For example, for the instantaneous rate of change at g1, the slope of the tangent for that point is going to be 1 times 8, 8. And then for negative 3, it would be negative 24. I've been using a vocabulary of distance in this example, and thinking about rates of change in the framework of distance is an easy way to set up this conversation. But change doesn't have to be a change in position. It can be almost anything, like the rate at which something decays or oxidizes or expands. Let's look at another equation that is tied to the rate of change in population and circle back to that second technique I mentioned. Let's assume that the function p of t is equal to 1.15 times 1.014 to the t power, where t is equal to the number of years after January 1st, 1993, will give you the population of China. So right off the bat, you can see that this equation is modeling exponential growth. If we plug it into Desmos, you can see visually how the rate of change is accelerating over time. The other important note is that because the variable in this function is an exponent, I don't currently have the tools to figure out the derivative algebraically. We can still use the formula to compute averages, though. For example, if we wanted to know the average rate of change in the population between January 1st, 1993 and January 1st, 2000, we can just plug the function into our equation and compute. For January 1st, 1993, t is going to equal 0, and January 1st, 2000 is 7 years later, so we'll just set h equal to 7. We calculate the populations at those two dates as 1.2675 billion and 1.15 billion. Then we subtract the 1993 population from the 2000 population, and then we divide the result by the number of years to get an average rate of change of 16.8 million people per year. I can't algebraically determine the instantaneous rate of change for this function, but I can still see that the instantaneous rate of change is always increasing. When we look at the average rate of change that we just calculated, we can be sure that the instantaneous rate of change on the last day of that period is higher than it was on any other day in that period. So we can be sure that it's higher than the average as well. No matter where we put A and B, as long as A is before B, then B is going to have the higher instantaneous rate of change. As long as we know the value of A and the period that we want to measure the average over, we can use this formula to determine an average rate of change. For example, if we wanted to know the average rate of change between January 1st, 2012 and January 1st, 2022, all we would need to do is set the A to 19 and H to 10 and compute. So that gives us a population in 2022 of 1.721 billion and a population in 2012 of 1.5 billion, the difference being 0.223 billion. And we'll divide that by 10, and that gives you an average rate of growth of 0.0223 billion people, which is 22.3 million people a year. So with such a robust tool for quickly and easily determining average rates of change, surely we can figure out a derivative even without algebra, right? Kind of. As I mentioned, I don't currently have the tools to determine the instantaneous rate of change for this function because the variable for the function is in the exponent. As a result, I can't get the h out of the denominator, so when it goes to 0, which is the point where the average turns into the instant, my result is undefined. What I can do is observe that the graph doesn't have any blanks or jumps. The domain appears to be all real numbers with nothing skipped. I can deduce that the instantaneous rate of change for any given moment is going to be higher than the average rate of change for the period preceding and including it, and lower than the average for the period following and including it. If I calculate averages on a smaller and smaller interval, getting closer and closer to having an h of 0, it should be possible to determine an instantaneous rate of change. Just for fun, we'll ask what the instantaneous rate of change should be for today, February 7th, 2023. Today is the 38th day of the year, which I'll convert to a decimal by dividing it by 365, and that will give us 0.103, which I will round down to a nice 0.1. So A is going to be 30.1. Using Desmos, I'll put together a quick table showing the average growth rate between today and a date up to 1 year away, both in the past and in the future. The numbers start to converge very quickly, and even though I can't say for sure what the instantaneous rate of change is, I can say with some certainty that it is going to be between 24,296,602 and 24,296,636 people per year. There's no world in which this model has that kind of precision, so if I round it to 24.3 million people per year of population growth, no one's going to argue. For purposes of translating the number into a tangent line for this function, don't forget to convert it back into billions, i.e. your slope is going to be m equals 0.0243, not 24.3. So thank you for watching all 10 minutes of that. If it felt excruciating to watch, just understand that it was even more so to make. I still have a lot of questions about the chapter and about some of the things that I clearly have gaps in my background knowledge, but I think this part of the module, the calculating the derivative, feels like it makes sense. I'm feeling pretty good about it, but I am eager to see if anybody has any thoughts or comments on how I went about attacking the problems and how I, kind of characterize what it is that we're doing. So thank you and good night. Okay, I'm back with my first of hopefully not many corrections that I'm going to need to make to this particular post for community problem number 1. After reading some of the other contributions that my classmates made, I realized that I had put in the slope of the tangent, but I had failed to actually put in the equation for graphing the tangent. So without further ado, here is correction number 1, how to actually calculate the equation of the tangent line. So what you do is you take y minus y1 equals m times x minus x1, where y1 and x1 are just the point that you're trying to find the tangent for. So in this case, that's going to be p 30.1. The 30.1 is the t value for today, 30.1 years after January 1st, 1993. So we plug in the y and the x values for where that would be on our graph, and then we calculate them out. So p 30.1 is going to equal 1.747 in billions, and m, which I already said is the derivative, that's the slope, so 0.0243 is our slope. Plug those numbers in, distribute the m across that equation, and then move this negative 1.747 over to the right, and that is going to give you the equation of the tangent line. So sorry I left that out. Thank you everybody else for getting it right so that I could kind of copy your footsteps. Obviously something I need to review on my own time before the quiz. So thanks and good night.